Thank you everyone for joining today. My name is Ryan Brennan. I'm president of Glass Expansion's US office. I'm going to be the moderator today for today's webinar titled Mastering Trace Metals Analysis, Understanding the Factors that Limit ICP. I'm pleased to introduce you to my colleague, our presenter today, Maja Budanovic, is our product manager at Glass Expansion, supporting customers throughout Europe, Middle East, Africa, and Central Asia with ICP sample introduction solutions. She holds a PhD in analytical chemistry from Nanyang Technology University in Singapore and has over 10 years of experience across research and industrial environments. Maja has co-authored 13 peer-reviewed scientific publications, and prior to joining Glass Expansion, she worked as a regional application scientist at Thermo Fisher Scientific, supporting trace element analysis applications.
Well, thank you, Ryan, for the introduction, and thank you, everyone, for joining us. So as Ryan said, today we will be discussing some of the key factors that can influence your ICP performance. So many of the challenges we see in the lab are not necessarily related to the instrument itself. Very often, they are influenced by small details in your sample introduction system. So from how the sample is delivered to how efficiently it reaches the plasma. So to start, we will first consider the sample delivery system as a foundation of the ICP analysis. So basically, any instability introduced here can directly affect the signal quality and the precision. And in this table, there are some of the main factors that can influence the sample delivery. So the first one is a sample optic stability. If your sample flow changes over time, the amount of the aerosol that is generated will also change, and that can result in a signal variation. So basically, we need to have this stable pump flow and a leak-free tubing connection. And the next factor is the particle transport. So as you already know, the samples are usually not perfectly clean. So depending on application, suspended particles or precipitates or even the dust from environment can enter the sample pad and contribute to the blockages. Another important factor is a carryover. Any residual sample that remains on your sample probe or within the flow path can contribute to this carryover, and that will affect your subsequent measurements. And the next factor that I think it's often underestimated is a bubble introduction. So even small amounts of the air that can enter your sample pathway can create these temporarily changes in your sample flow that will result in signal fluctuations or spikes. And the sources of that bubbles can include the loose connections, tubing installation issues, or even insufficient priming. So just make sure to have the appropriate tight fitting and with the minimum dead volume. And now one component that is a key for a reliable sample delivery is the sample probe itself. There are several challenges that can be overcome with the optimal sample probe selection. So the first one is the particle management. So as we mentioned before, many real samples contain suspended particles or even small precipitates. And the larger particles can enter the sample flow and cause either the partial restriction or blockages. And for example, here we have the Guardian probe. This is the latest design that we have for the sample probe. And this Guardian probe can address these issues caused by the particulates by using this ceramic tip with the control microhole structure. So these openings here that you can see, they act as a particle barrier, helping to reduce the risk of particles entering the tubing or the nebulizer or other components. And another restriction or another consideration that we can look into when we think about the sample probe is maintaining the sample integrity during the movement of your sample probe between the vials. So features such as the control drainage and the flare collar design can help reduce these residual droplets and carry over during this sample transfer. And we will see this a bit later in the video representation on the following slide. And finally, the mechanical robustness is also very important because the probe is repeatedly moved and positioned, and it's also often exposed to the different sample matrices. So using the ceramic robust cone tip helps guide the probe into the vial openings and reduces the risk of damage from the minor misalignment. Now, in this short video that I mentioned, we will compare the wetting behavior of the two sample probes, so the Guardian probe and the previous designed PTFE carbon fiber probe. And we are comparing it for the aqueous application. So we have added a dye to a 2% nitric acid solution just to make this liquid movement a bit easier to observe. And as you can notice here in the video, the Guardian probe demonstrates improved wetting behavior and a drip-free performance. And the next thing that I want to talk about in the sample delivery is the internal diameter of the sample line, because this one is also important as the different applications may require a different IDs, internal diameters of this sample line. For example, smaller diameters can reduce the sample consumption and improve your washout, while the larger diameters are kind of more suitable for the challenging matrices, such as the high TDS, because it can reduce the risk of the restriction and blockages. And now from the design perspective itself, when you have these interchangeable sample lines, you have actually flexibility to optimize your sample delivery system without needing to replace the entire probe. Because in the contracts, the PTFE carbon fiber probe that we saw in the video before, that probe had this sample line permanently fused to the probe, so it cannot be simply replaced. And this means if a blockages occurs anywhere in this line, where is usually most likely to happen, the entire probe typically needs to be replaced. And here on this slide, I just also want to mention that some of the applications with a more difficult sample types may need additional protection from these particles and from the blockages, where the Guardian inline particle filter can help. And it can be used in combination with the Guardian probe or with any other sample probe to remove a larger particles. And you can find more details about this Guardian inline particle filter by clicking on the image provided here. Next, we need to consider the internal diameter of the pump tubing that also directly influence your sample uptake rate. So selecting the correct tubing side depends mainly on the application and your required sample flow conditions. So smaller IDs are typically used for precise low flow applications, for example, for your internal standard. And then the larger diameters are used when a higher sample delivery rates are needed, and also for the waste to ensure the efficient drainage. And another factor to consider here is a pump speed. So the combination of the pump tubing ID and the pump speed determines your actual sample uptake rate. So these two parameters should be optimized together. And to support this, you can visit the sample uptake calculator on our website, which can be used to estimate your flow rates based on your tubing selection and the pump conditions. And here I included some of the practical recommendations. So in general, the condition of your pump tubing can directly influence how consistently your sample is delivered. And this tubing with the time wears or flattens, the flow rate can be unstable, which usually leads to the higher RSD values. So for the routine maintenance, we recommend to regularly inspect the pump tubing for any signs of wear, such as the cracks, discoloration, and basically replacing those pump tubing based on your usage and the sample metrics. It is also very important to maintain this correct pump tension and your roller alignment on the pump, because if you use excessive pressure, it can shorten the lifetime of your tubing because it will accelerate the tubing wear. And a simple step that can help extend your tubing lifetime is keeping your pump rollers properly lubricated. And you can use this Easy Glide cloth to reduce the friction between the rollers and the tubing. The next challenge is ensuring that any additional components, such as your internal standard, is introduced consistently without adding any variability. So any small leaks, inconsistent connections, or contamination can affect the amount of the internal standard that reaches the plasma and may lead to inaccurate internal standard correction. Here we can see the Trident CT that is designed to provide the consistent mixing between the sample and internal standard solution. One of the very important design feature is the CT, which stands for the constant torque, and the constant torque zero dead volume ratchet fittings that you can see here are used for all three connections. So for your sample, for your internal standard, and for the outlet towards the nebulizer. And this ratchet style reduces the variability that is usually caused by inconsistent tightening. And very importantly, it's a secure connection that minimizes potential leaks. So the ratchet, how it works, when you activate the ratchet mechanism with a click, you will not longer over tighten this connection. And here, if you want to or need to understand how much your sample or internal standard is diluted, you can use this Trident dilution factor calculator that is available on our website, and it can provide you the estimate of this dilution factor based on the selection of your tubings. Now, after the sample delivery, the next very critical step in the sample introduction is the aerosol generation system. And for aerosol generation, I'm considering the combination of your nebulizer design and the spray chamber design. So during the nebulizer process, a wide range of the droplets are usually produced. However, only the smallest droplets that are typically below 10 micrometers are eventually transmitted to the plasma, while around 95 to 98% of the nebulized sample will be actually drained as a waste. And this is why this aerosol generation has such a significant impact on ICP performance. And now if we want to consider the factors that can influence ICP variability, the first one is the droplet size distribution. So the smaller droplets are transported more efficiently and they require less energy in the plasma. While if you have a larger droplets, they can increase the solvent loading and reduce your plasma robustness and stability. Next is the aerosol uniformity. So with an ideal average droplet size, fluctuation in the aerosol production can lead directly to fluctuation in signal intensity. So basically, what I'm saying here is that we need to have a stable gas-liquid interaction and consistent nebulization. Another important parameter is the sample aspiration rate. So here, we often think that the higher sample uptake will improve the sensitivity, but it will not necessarily improve your sensitivity. Why? Because if you have too much of the solvent, that will increase the plasma loading. And then on another side, if you have too little, that will reduce your analyte transport. So basically, the optimum aspiration rate will depend on your nebulizer design and your application. Next very important one is the nebulizer gas flow because it controls this primary aerosol formation and its transport. So if we have a too little gas, that will produce a larger droplets, which we don't want to have. But while if you have too much of it, it can reduce your transport efficiency. So for the optimal nebulizer gas flow, this needs to be in the balance. And lastly, sample metric properties such as the viscosity, dissolved solids, and organic contents all influence your nebulization, which is why different sample types often require different operating conditions and different sample introduction setup. Here we can look a little bit more into the design parameters of the nebulizer. It influences the primary aerosol generation, such as the gas orifice geometry that will control the gas velocity of the argon entering the nebulizer and eventually affecting the sensitivity and the transport efficiency. So this high gas velocity creates these shear forces that are required to break the liquid into the droplets. And any small differences in this gas orifice geometry can significantly affect droplet size distribution. And the second is the liquid capillary dimensions that can influence your sample uptake rate. your pressure drop or flow stability. So that's why the precision manufacturing is essential here. Then the actual atomization nebulizations process occurs where the gas meets the liquid. And this introduction determines the initial droplet population before the further operation. And another often overlooked factor is the manufacturing consistency. So very small differences in concentricity or the capillary alignment can change the aerosol characteristics. And this is why the manufacturing tolerances, some of those you can see here for our nebulizers, those manufacturing tolerances are critical for the long-term reproducibility. And lastly, of course, your material selection also matters because it influences the chemical resistance, contamination risk, and the operational lifetime. Now, many ICP performance issues can be tracked back to the problems with that nebulizer operation. So the common symptoms, such as poor sensitivity or high RSD values, can have several causes, including the partial blockages, unstable gas flow, incorrect installation, or issues with sample delivery. And usually the useful first step is always to verify the aerosol production. If the aerosol is weak or inconsistent, the next check should include your nebulizer back pressure, the gas connections, and the nebulizer tip conditions. Because the high back pressure often indicates any kind of restrictions caused by salt deposits, particulates, or dry residues. And on another hand, the low back pressure may indicate a leak or a damaged nebulizer or a tubing issue. And in the case that you do not observe any aerosol production, it could be due to the damage on the nebulizer tip itself or some kind of complete blockage. And for all blockages, it's important to identify the blockage location, clean it, or replace the affected component. To summarize some kind of troubleshooting sequence, first check the aerosol production, then verify nebulizer pressure and gas connection. After that, inspect for the blockages, clean or replace components if damage is confirmed. Besides checking the nebulizer itself, there are a few simple things that can help maintain stable performance. The first one is checking the argon connection. So if you start seeing any increased RSD values or unstable signals, a small gas leak at the nebulizer connection could be one possible cause. And that's because over a time, if you have polymer tubing, that can become harder and may no longer provide a good seal. And another simple check is sample uptake that we mentioned before. So if you are unsure whether the sample is being delivered correctly, you can observe the movement of an air bubble in the uptake tubing. The travel speed can give you this quick indication of whether the uptake rate is in expected range. And finally, the nebulizer should always be stored in their protective case to prevent any kind of dust or the particles from entering the capillary, especially when they are not being used for some time. So once the primary aerosol has been generated, it enters the spray chamber that removes the significant proportion of this primary aerosol and then creates a tertiary aerosol. And here the droplet selection is important because the larger droplets contain more solvent and can negatively affect your plasma stability. Then we have the internal volume that controls the aerosol residence time and system response. So larger volume chambers can provide additional time for droplet separation, while the smaller volume designs are often optimized for a faster response and efficient washout. And the next is the chamber geometry that can influence how the aerosol moves and circulates inside the spray chamber. So the good geometry helps maintain the consistent aerosol transport and improves your precision. Then we have a drainage that is also important because the excess liquid needs to be removed efficiently. So any poor drainage can lead to the liquid accumulation inside the spray chamber that can cause this pulsation and the signal drift. And here in this image, we can observe the design of the double pass twisted spray chamber. So for example, in this design, we can see this intended groove that is built into the top of the spray chamber. and it serves as a barrier, preventing solution from being simply swept into the torch. And this position and the depth of this groove is critical. Also, here we can see another design feature, which is the walls of the chamber that has this vertical region for the efficient aerosol generation and to maximize this transport efficiency to the torch. Another design feature that we can see here is the Helix CT, the nebulizer spray chamber interface. This Helix CT was developed to address some of the common limitation in the traditional spray chamber interfaces, particularly around this nebulizer connection, taking into account the dead volume and reproducibility. So one important feature is the constant torque locking mechanism that provides the consistent sealing force every time, which helps avoid any issues that can be caused by over-tightening, such as the damage to the nebulizer or the inconsistent positioning. And the PTFE press fit seal provides a chemical resistant connection without relying on any traditional O-rings, which can degrade when they're exposed to any aggressive acids or organic solvents. And another key design of the Helix CT is the zero dead volume interface, because by minimizing the space around the nebulizer, around this nebulizer connection, the residual sample will be reduced, which will help improve the washout performance and reduce a carryover. And the results here, they show that with the Helix CT nebulizer interface shown here in the red for the 10 ppm lubidinium standard, we can see that it can be washed out in as little as 4 seconds compared to the here in the blue non-Helix interface that needs around 16 seconds. Next about the spray chamber is you can optimize the spray chamber design in the terms of the volume. And the main objective is to improve the aerosol transport while maintaining the precision and, of course, efficient washout. One way to do this is to reduce the internal volume of your chamber. And the Tracy BC, the ball connection, it's a high efficiency spray chamber that is based on this concept. So it uses a 30 ml cyclonic design to balance efficient removal of the large droplets with a fast washout performance and also faster response when changing between samples or conditions. So for the washout performance, mercury is a good example due to its tendency to show this memory effect. So here we use the 1 ppm mercury solution and the Tracy BC spray chamber, so the latest design of the high efficiency spray chamber, demonstrates the much faster signal recovery, reaching the low background levels approximately 64% faster compared to the double pass cyclonic design. Now, when you need to use the HF in your sample preparation or analysis, you would need to have the inert spray chamber. And previously, that was a 50 ml PTFE trace spray chamber. However, now the latest design, which is the Tracy BC Peak spray chamber, is a 30 ml high efficiency spray chamber. And as mentioned before, the smaller volume design allows for the reduced residence time and more efficient aerosol transport to the plasma. Also very important is the material, because the peak material here, in comparison to PTFE, maintains these consistent wetting properties during this routine laboratory cleaning. And peak, unlike the TFE or PFA spray chambers, does not require internal surface treatment, which simplifies maintenance. And here we can see the comparison of the average intensity and also RSD result from the 41 optimization checks by a specialty chemical manufacturer in the US using the PEAK and the PTFE spray chambers. And as you can see, the results show the significant increase in the signal intensity for the lead, arsenic, and manganese with the Tracy BC PEAK spray chamber. And now let's look at some of the common spray chamber issues, what might cause them, and what can we do to address them. So if you ever observe the poor sensitivity or a signal drift, one possible cause is inefficient aerosol transport due to any kind of deposit building up inside the spray chamber. And the first step are to clean the spray chamber and check that the nebulizer is installed correctly. Then for the poor precision or a higher RSD, The issues can be related if you see any kind of droplets accumulating of the spray chamber walls, which can make the aerosol transport less stable. So usually cleaning the spray chamber and checking that the system is draining properly can help. And then if you experience any delayed washout or any memory effects with some elements, sample may be remained in the spray chamber or in the drain line. And in this case, it would be important to inspect the drain tubing and maybe considering the increasing the rinse time. Another thing that can happen is excess liquid that entering the plasma. And this can happen if the spray chamber outlet is blocked or the drainage is not working properly. And now I wanted to mention some of the hidden causes of instability because they are often overlooked because they are these small, not small, but they are connection related issues. So leaks, loose fitting, or incorrect base draining settings, sometimes the warm pump tubing, or even the blocking lines can all affect your sample flow and introduce this air into the system. And there are a few quick checks that can help identify these problems. So first one we already kind of mentioned, which is the free flow test to check the fine steady mist from your nebulizer. Next is to check your drain flow if it's draining smoothly. And also performing this visual inspection to check for any signs of the bubbles of or the wet fittings or visible leaks. So how you can minimize these issues from happening is using these zero dead volume connections, such as the Unifit and Helix City that we mentioned before. We recommend them to use at the key connection points of the sample introduction system. So between your sample line and the nebulizer, between the nebulizer and spray chamber, and also here at the drainage outlet of the spray chamber. And another often overlooked factor is the correct installation of your nebulizer inside the spray chamber. So as shown here on this example, both nebulizer depth and tightening torque influences your sensitivity. Because if you over tighten, because you're very strong, this connection, that can result in your sensitivity drop. Here I just put the example of the arsenic because it's a very important element for the ICP analysis. We can see sensitivity drop with the over tightening, so with the higher torque. And how you can prevent that is by using this constant torque mechanism on this connection. And now for the last section of today's presentation, we will move to the plasma interface, the third stage. This is where the aerosol enters the plasma environment and where the actual conversion of your sample into the atom ions excited species take place. So the torch and the injector, they define how efficiently the aerosol is introduced into the plasma and how consistently the plasma can process the sample. One of the most important factors is the injector geometry, actually, especially the internal diameter and its design, because the injector controls your aerosol transport and how efficiently this aerosol penetrates into the plasma, and also how long the analyte remains in this high temperature region. So incorrect sizing can lead to the poor atomization, reduced sensitivity, or the matrix dependent effects. The injector material also plays a role because materials such as the quartz, alumina, or sapphire can have a different chemical compatibility, different heat resistance and memory behavior, which can be very important for these aggressive sample types. And then we have, of course, the deposit or blockages that can happen inside the injector, and that can change the aerosol pathway and your gas flow, and it will cause any kind of signal drift, also higher backgrounds and the poor precision. And the next is the torch condition that is also equally important, but we will discuss that on the next slides. So torch failure can result from any gas leaks, damage, or misaligned RF coil. So for example, plasma instability, or if you have any kind of difficulty to ignite your plasma, that can be caused by the gas leaks. It can be caused by the worn O-rings or even the injector ferrule deformation. So the first step would be to inspect these connections and if they are damaged, to replace them. Then we have a poor sensitivity or any signal drift that can occur when the injector becomes partially blocked, like we mentioned before. For example, that happens if you have a high salt deposit from the high TDS samples. And in this case, inspect the injector tip, clean it, or replace if it's necessary. Another thing that you can consider is adding this kind of helpful accessory, which is the Allegra Argon humidifier, because that can help you to reduce the salt deposition. If you observe the frequent torch cracking, or you observe that the lifetime of your torches become shorter, this can be related to the RF coil damage or misalignment, which can cause uneven plasma heating. So the RF coil should be inspected for damage, for any discoloration, cleaned or replaced if required. And the next very often happening is the outer tube devitrification that can be a result from the chemical attack or a prolonged high plasma temperature. So basically you can see it as a clouding or the crystallization on your outer tube, and it should be inspected and replaced if necessary. So overall, remember that the torch performance depends not only on your software operating settings, but also on the physical condition of the torch, of the connections, and RF coil. So any poor mechanical connection can still cause a flow instability and the plasma issues when the gas flows are even if the gas flows are correctly set. Now here, let's look at some of the torch solutions for a bit more challenging sample matrices where the standard quartz torches may experience the reduced lifetime. So any applications such as of the soils, wastewaters, high acid digest, organics, and others can create this additional stress due to the high salt contact or aggressive chemicals or increased plasma loading. And one way to manage these challenges is by using a latest demountable torch design. And because with this demountable torch design, instead of replacing the complete torch assembly, you can replace the individual components, such as the outer tube or injector. And this helps to reduce your maintenance costs and improves the flexibility for different applications. So injector configuration can also be selected depending on your sample type. So usually the large bore injectors, 2 mm or larger, are designed for the high TDS samples where higher sample loading is expected. Then the ceramic components such as the alumina are used for HF containing samples, and the platinum or the sapphire injector are usually suitable with a highly inert, where kind of highly inert materials are needed. And on these two images, we can see the latest design of the e-torch that follows the same principle as our D-torch, providing this demountable design that allows greater flexibility and easier replacements of individual components. And another important feature is the ferrule-based design, which can provide secure injector positioning and a fewer leak points. Now, for some of the applications, the main limitation of the quartz torches is degradation caused by these aggressive chemicals or high salt deposits, or even prolonged exposure to high plasma temperatures. So these conditions can lead to what we previously mentioned, the vitrification of quartz, which appears, as you could see on the previous image, as a clouding or crystallization of the outer tube. So for these challenging applications, what you can do is to use a ceramic outer tube because the ceramic material can provide the improved resistance to the vitrification itself and also helps to maintain the plasma stability during this high matrix analysis. And in this table, in the comparison between the standard quartz tube set and the ceramic outer tube set, we can see that the ceramic configuration shows the increased sensitivities. And here we have the example of some of the elements such as the zinc, nickel, and manganese. The second major factor in plasma interface region is the RF system that provides this energy that sustains your plasma. And any change in energy transfer directly affects your ion generation and signal stability. So one common issue with the RF coils is the corrosion. And this can occur over a time because of the heat exposure or the chemical oxidation. And then if that occurs, the corrosion can result in reduced energy transfer efficiency, increased load on your RF generator, or in less robust plasma. Also, the corroded coils may create this kind of hotspots that can lead to premature torch failure or even melting. Next, the alignment of the RF coil is also very important because it will help maintain the correct plasma shape and position. Then here we can see, so there are different coil materials and the plating available. For example, copper coils are copper coils are more like kind of cost effective, but they can, because it's a copper, they can oxidize more quickly. Then we have a silver plated coils that can provide high conductivity, but they're a bit more prone to the tarnishing. And we have a gold-plated coils that offer a better corrosion resistance, and they're more kind of suitable for the harsh environments. And to maintain this a consistent performance of your RF coil, it's very important that you inspect the RF coil, that you clean it periodically to remove the deposit or any signs of this oxidation. And if your RF coil shows any signs of this severe tarnishing or damage, it should be replaced because it can prolong the lifetime of your torches. And we came to the end of today's talk. And Klaus, if you have any questions about your sample introduction system or would like to discuss any specific application challenge in more detail, you can contact us at the GmbH@gicp.com. Thank you.
Thank you, Maja. Excellent presentation, right on time. So we have just about 10 minutes for questions. So with that said, Maja, I'm gonna go ahead and start to ask you a few questions. So the first one here is, can the Guardian probe and filter completely prevent particles from reaching the nebulizer?
Thank you, Ryan, or thank you for the question. So basically, the particles that are larger than the microholes on the ceramic tip that you can see on the Guardian probe, those will remain in your sample vials. And similarly for the Guardian inline filter, that filter has a pore size of the 120 micrometers. So larger particles will be retained by this filter. And these large particles that are removed by the Guardian probe and the Guardian filter, so those are those size of the particles, these large particles, are typically the ones that cause the blockage in your sample introduction system, so in your nebulizer, sample line, or other components. Now, all the kind of smaller particles, they're less likely to cause a permanent blockage, but what can happen over time, they can accumulate in some of the sample pathway. So what we do usually recommend is just to keep to maintain and clean your inline filter and the nebulizer regularly.
Thank you, Maya. So this one kind of relates to the same question with regards to the particulates in the probe. What is the best way to clean the sample probe?
Okay, the sample probe, usually the best way and what is enough for cleaning of the sample probe is just using the online cleaning method, which is starting your analysis and finishing your analysis by aspirating and introducing blank solution or blank solution, for example, 5 to 10 minutes. And then you would also rinse it with ultra pure water or the deionized water for 5 to 10 minutes. So that's so-called online cleaning that should be usually enough. And then if you consider the Guardian sample probe in particular, we would not expect the cleaning that's to happen very often in a regular basis because all of the particles that are larger than these microholes will remain in this sample vial. And then what I can think about that can happen, maybe if any blockages happens, usually it's more likely to happen in this sample line. So what you can do, you can check, maybe inspect it with any kind of magnifier to see where exactly the blockage happened in that sample line that is connected to the sample probe. And then that can, if it's at the end, maybe it can be removed by cutting, or if it's at the beginning, closer to the sample probe, you can simply replace it if you have a Guardian probe to use these interchangeable lines. If you have just the standard, the carbon fiber probe, and really some kind of blockage do happen, one thing that I can think about you can do is you can backflush. So basically by reversing your pump in another direction to try to remove it. And if it's at the tip of your sample probe, you can also try to soak it in any kind of surfactant or detergent diluted detergent solution.
Thank you, Maya. There's staying on the topic of maintenance. There was two other questions that came in. If you could give some advice on what are good methods for cleaning your torch and spray chamber.
Okay, let's start for the torch. So for the torch, I would usually first determine, by the way, when you're looking at the torch, I would determine what I think from knowing about my sample type and seeing the torch, what I think where the deposit comes from. Of course, if it's the organic, like a carbon deposit, it will be usually if you have the muffle furnace, you would just put it under 500 or so degrees for some amount of time to get rid of it. But then if you have any aqueous analysis, so aqueous type of the samples, you can look into is the deposit caused by the salt. And if it's a salt, usually it can be recognized by this white remaining deposit on your outer tube, and that can usually be removed just by soaking in the. We kind of use the RBS 25 Fluca solution that works very well if it's a salt deposit. And then if you do have some kind of metallurgical samples or you think that the deposit comes from any kind of metals, you could also soak your outer tube, that portion that is dirty and needs to be cleaned. You can soak it in the acids that you use for your sample preparation. Of course, not considering HF, but that usually helps. And in the spray chamber, let's say in the ICP-OES, you can easily see sometimes when these droplets form inside the walls of your spray chamber, and you usually can soak it also in some kind of detergent, diluted detergent solution. And basically, you always need to consider how much and how strong cleaning, how aggressive cleaning it needs to be. That's how you will see how much you should dilute this surfactant or detergent.
Thank you, Maya. So this question came in when you were talking about spray chambers, and they specifically have asked, room temperature will affect the results. If yes, how do you maintain the temperature? So I'm assuming this person might have, maybe they have some issues with the temperature control of just the laboratory environment itself.
Yeah, of course. I did not mention the temperature on the spray chamber, but the temperature definitely does affect your results, especially if you have like a huge fluctuation inside your lab. You can experience some kind of the fluctuation in your results. Again, depends about how much of that room temperature differences you observe in your lab. That's why usually in the ICP-MS you will have a control temperature, and in ICP-OES, what you can do, you can use this device. It's called ISOMIS. That can help maintain. You can set up the temperature that you want, because if you're having like if you want to have like a higher sensitivity, you can set up this device. You can set up the temperature to be higher, for example.
Thank you, Maya. So this one came in while you were talking or focusing on nebulizers, so nebulization efficiency. And somebody asked, how do you verify aerosol production? Is it purely a visual check?
So I did talk about the visual check in the sense like that you can check this free flow for the nebulizer to see if you have like this fine steady mist kind of creation. That's like kind of a visual check. But of course, any kind of nebulization, if something goes, if it's not like ideal, if it's not like optimal nebulization, you will see it in your results. So it can be like higher RSDs or changes in your sensitivity. And sometimes these droplets that I was talking about, the size of the droplets and stuff, you might not be able to see it very well just by visually observing, but you can see in your results. So any changes in what you're probably for accuracy, you would check your internal standard recovery nowadays, online internal standard recovery, and also the RSDs.
Thank you, Maya. Let's see. This is a good one. So somebody has a question specifically about gold and mercury. They're wondering if you could give any advice on measuring specifically low concentrations of gold and mercury. They don't specify whether ICP-OES or ICP-MS, but still.
Okay. So for the mercury, it's interesting element. I did actually my PhD on that mercury in the air detection. Not easy sometimes, especially, depending what kind of sample type you do have, and is it ICP-MS or ICP-OES? Of course, it has a difference. But basically, I was looking into getting rid of the memory effects from the mercury that sometimes can happen. There is a different way of doing so. So usually many research are done that. And one of the methods that did work the best for me is actually using the gold standard if you can, but I guess you cannot because you asked about the gold and mercury. So I did use the gold, 1 ppm of gold to add in my standards and all and the rinsing solution. But just make sure if you cannot do that, there are the other sort of the stabilizing the agents that you can use in all of your standards and the rinsing solution to make sure that you're kind of removing this stickiness from your sample pathway. And I know that the Inorganic Ventures, for example, has this kind of true rinse solution that can help in particular in this mercury issue that I did not test by myself, but I saw the results that it works. So that's something that you can check.
Yeah, and Inorganic Ventures also has that really great interactive periodic table that element by element you can see like what different acid or basic solutions can kind of aid in the washout of those kind of sticky elements. That's a really helpful resource as well.
Yeah.
All right, so looks like we have time for one last question here.
Okay.
So this person asks whether the quality of the argon will affect the results of their analysis, and what are the main causes for the plasma impedance exceeding the working range?
Oof, okay. There was like a minimum quality and the purity of the argon that you need to use, and it's different for ICP-MS and for the ICP-OES. But of course, any kind of impurity or changes that can happen inside your cylinder or whatever argon you're using, it can affect your nebulizer performance, because if you kind of introduce any kind of impurities with it, it can affect how efficiently this primary aerosol has been created, produced, and also transported later. But Ryan, do you maybe have any? So usually I always had like the standard argon gas cylinder and stuff like that with a particular purity. I forgot how much the purity was, but
Yeah, I don't remember what the exact, and I think I do think that each ICP manufacturer might also have different like requirements for what level of purity argon you can and can't use. But if you do get a sort of a bad cylinder, it can basically result in you not being able to properly ignite your plasma. I've definitely seen that happen
yeah,
before.
I saw that in ICP-MS when you have like a liquid argon cylinder, it needs a little bit time for the pressure to adjust. Otherwise, you will have a problem in,
Yeah,
yeah, in
yeah.
igniting the plasma itself.
But so that brings us to the conclusion of today's webinar. I'd really like to thank everybody for attending today, and Maja, thank you for an excellent presentation. We did have a lot of questions come in right at the sort of the end there, so we definitely have some homework to do to get back to all these people. But everyone, thank you again for attending today, and we hope to see you again soon.
Thank you, everyone.
Bye.